All right, so we're looking at doing instantaneous velocity according to the title. And we got to do a little bit of adding of information onto this graph. So as of right now, we've got, maybe I'll just change the lighting just a little bit just to improve that shadow. As of right now, we got a curve on the page, but we don't have a story for it yet. So I think I want to rotate the page a little bit, and I'll give myself a little bit of breathing room for numbers. We've got position. Oh man, this must be a Monday because I've already had some sort of an episode with capitals. It's a capital offense. Thank you, Leo. I appreciate the sympathy. So, capital P. Oh no, somebody's left the cap off my pen. Position. I'm going to be a little bit extra. D with an arrow. Units of meters. And for argument's sake, we'll make north be positive for this one. And I'm trying to be the best me that I can be, so I'll underline it. All right, rotate that back. And then on the horizontal axis, we're going to have time in seconds. It's a scalar, no directions. And we'll just give this a simple title like position versus time. For an accelerating object. Okay, so nice and vague. We still need to set a scale for ourselves. So I think every 2 squares okay, so I'm not really telling a story that has any kind of context here, but I am going to say that every 2 squares we're going to have 1 second, 1.0 seconds. Maybe didn't give myself quite enough breathing room there. And then on our vertical axis, I think I'm going to go up by tens. So 1, 2, 3, 4, 5. I'm going to make this one be 50. One, 2, 3, 4, 5. 100. 1, 2, 3, 4, 5. 150. 1, 2, 3, 4, 5, 200. Okay, we got nice reasonable scale. Looks like my data doesn't go beyond 150, but I'm kind of set here. Now, we've got some things down below on the page in our organizer that we're going to be filling in. Instantaneous velocity, it looks like, acceleration, but I want to figure out the mechanics behind how we're going to get to that. And the idea that this is sort of a bit of a pre-calculus conversation is something that, kind of already hit on. It's called tangents. And if you have a curve like this, remember what we've done before is we found the slope of a position time graph where the position time graph was linear. But this is a non-linear position time graph. So we got to figure out, well, like, how could you find the velocity for a position time graph that's not a straight line? And that's not something we have to deal with very much. I mean, admittedly, as soon as I look at this, I'm like reminded of quadratics from grade 10, Like this looks like part of an upward facing quadratic. I could even talk about there being an intercept at like the 10 meter mark, this y-intercept here, but that's not the vein that I want to go down. What I'd like to do instead is I'd like to do what's perhaps the most romantic, the most enticing and exciting graphical analysis that there is. And it's called finding the tangent. And I'll show you what I mean by being sort of like, this like enrapturing exercise. What I want to do is just kiss this curve. I want to kiss the curve. And I want to kiss the curve, I think, at the 6-second mark. Right there. It's like going on a date, you know? If you ever get a date with somebody, if you ever get a date, make sure that as you approach your date, on first meeting them, you just kiss them at a single point. Notice that if I kiss them at more than one point at a time, that's weird. Also, it's called cutting the curve. And if you ever cut your date, you will not get a second date. All of this is applicable and transferable advice. So here we go. We're going to kiss the curve at one point. And if you kiss the curve at just one point and you don't cut the curve, then you should be able to see how my ruler here lines up with what the slope is at the dot that I've drawn so far. What I'm really doing is I'm finding the slope at that point in space. So here we go. I'm going to do my best. All right. Just kissing that curve at one point in space. Okay? I've done my very best. Now, I want to do a little bit of labeling. I want to label that this is the first point that I've considered, so that's going to be point number 1. I'll put a circle around that point. It's an important point. And I'm even going to say that since this tangent, and I'm like telling the story as a whole here, since this tangent tells me the slope at that point, I'm going to label that point my V1 point. Because if I can find the slope of this tangent, then I effectively am able to find out what the slope was at that point in space. Do you see what I mean there? This is almost like a zoom function. It's almost like I've zoomed in on that point and shown what it would look like if it was big. That's what a tangent is, okay? It just kisses the curve. Now, it looks like I'm going to be going through the 2-second mark. It looks like, I don't know, like I come pretty close here. Looks like I'm going to go through that point there. That looks like a nice, believable vertice that I pretty much go through. So I'm going to put a dot at those 2 points because one of the things that I'd like to be able to do is find the slope of this tangent. So I'm going to put a circle around that. I'll put a circle around that. Those guys are now points of interest for me. And I could say, hey, look, this rate triangle, which is actually a tangent and it represents the velocity at that one point in time, at the 6-second mark. Let me see if I can transfer some information down here. I've gotten a bit of information. I could say that I got V instantaneous. Let's just call this, we'll really make it pop out that this is position or time 1. V instantaneous at 6.0 seconds. Now, you wouldn't normally have like a form organizer like this. I'm just trying to demo how I would think out how to organize myself. I could calculate V inst, and I could even call it V inst 1 because I called it V1 up above. V inst 1 is equal to D2 for the tangent minus D1 for the tangent divided by T2 for this tangent minus T1 for this tangent. Now when I talk about D2, it would be the position at that second dot. D1 would be the position at this first dot. Of course, it never really was at either of those positions at those times. We're just talking about the tangent, right? We're pulling information off of the tangent for this. And then T2 would be for the second dot, T1 would be for the first dot. And so if I'm going to sub in my values, I'd say, okay, well, D2 looks like it's 60, 70 meter mark. D1, 0 meters. T2, 12 seconds. T1, 2 seconds. I'm going to have to pop this up here. I guess I should have arrows over top of each of these guys because they're vectors if I'm being really good about things. But 70 minus 0 is 70. 70 divided by, well, 12 minus 2 is 10. Isn't it just 7? 7.0 meters per second. And in case you're worried about the units, look, meters in the numerator, seconds in the denominator. So 7.0 meters per second. And we could even say 7.0 meters per second north, because we said north was the positive direction. So that's my first attempt at a tangent. My second attempt at a tangent, I'd like to do a tangent of a different color because I always have a hard time keeping track of like all these tangents. By the way, you guys are gonna have to, in a future lab, you'll have to do like 5 tangents on one graph. So here I am. Maybe you can't tell because the color quality of my camera, but this first tangent was purple. My next tangent I'm gonna do is orange. Otherwise, this is just gonna look like a spider web of tangents, okay? If you do like 5 of them, and for the lab, you'll have to do like 5 of them, okay? So I wanna do it at the 10-second mark. People say, well, why are you gonna use the 10-second mark? Well, it's an arbitrary choice at this point. I would suggest that when you do a lab, space your tangents out equally, you know, like every 2 seconds or something like that. I'm just gonna do a second tangent at the 10-second mark. So it's gonna be one that kisses the curve at that point in space. So again, the romantic dance of the tangent. I come up. How many points do I kiss my tangent at? 1, not 2, right? No second dates otherwise. So we come up and we kiss this tangent at 1 point. There we go. That look like a good kiss point? All right. I feel like this is so satisfying. I love this. All right. All right. Now my orange, I feel like it's not going to show very well on camera, so maybe I'll just switch it over to red. I feel like it'll be a little bit darker. And I've done my very best. Remember, this is an approximation method, so if yours was ever so slightly different than mine, it would be okay. Because really, that's why we're going to do 5. If you do multiple tangents, then the effects of these tangents and the fact that it's a human approximation method are going to average themselves out, okay? All right, so I've got myself a tangent. I say, okay, well, I'm going to choose 2 points that are far from each other, and strategically, I'd like those 2 points to hit vertices. Turns out that this one happens to hit a vertice on the grid lines. This one happens to hit a vertice more or less on the grid lines. I'm going to choose those 2. I think they're pretty good. I'm also going to label this up. I'm going to say, well, if the first one was V1, I'm going to call this one V2. It's the velocity that happens at time 2. You know, like if I want to really like make this pop for myself, I could put like a really dark dotted line down here saying, hey, look, that V1 happened at that moment in time. This V2 happened at that moment in time at the 10-second mark. And while I'm thinking about this, maybe I'll write that I'm going to look for the instantaneous velocity at the 10-second mark. And so when I go to do the math on this one, I'll say, okay, well, V-inst at time 2 is equal to that D2 minus the D1 for the tangent that I've created for the instantaneous velocity for moment 2, divided by T2 minus T1. Remember, these D2s and T2s, D1s and T1s are specific to that tangent, okay? So they don't belong to the other tangent. I know that I've used D2 twice. I just don't want to add a whole bunch of extra subscripts and confuse myself as a reader, okay? I know that the red stuff belongs to the red tangent, and I'm okay with that color coding. So I sub in my D2 and my D1 for that guy. It looks like D2 is going to be 110 meters. D1 is going to be 0 meters again. That's always handy. T2 is going to be the 13-second mark. Nice prime number. And T1 is going to be 2.0 seconds. And I'm going to pop this up to the top. I'm trying to save myself a little bit of space for some stuff I want to do at the bottom of the page. And it looks like the V-inst 2 is going to be equal to, somebody with a calculator, help me out. What's 110 divided by 11? What is it? 13.75. Beautiful. Thank you, Leo. Meters per second. And I mean, if I was really stuck on sig figs here, I could round it off to 3 sig figs. Yeah. Oh, did I make a mistake? 13.0. Oh, you guys caught me. This is the nice thing about having people that can help me. Thank you, proofreaders. This should be a 5. So let's try that again. Did you give me the right answer and I wrote down the wrong thing? 8. Oh, he divided by 8. Okay, good. At least we have the right answer. So Leo beat my typo. Okay, so we could say that it's approximately 13.8 meters per second. Looks like we're dealing with Look, the denominator would end up being, oh, it would be 8.0, so I really have to round it off to 2 sig figs. Oh my gosh. So approximately 14 meters per second. Doesn't really matter because it's not going to carry forward in our next layer of calculations anyway. But 14 meters per second, and it would also be to the north because it's a positive value. All right. I want to make a little word note because I know that some people thrive on words. Let's just make sure that we have this in words. A tangent is a way to find the slope at a single instant. And it's particularly useful for curved graphs. For curved graphs. Now, for those of you that have reached ahead and they're doing the calculus, if I had this curve as an f of x function, and I know that most of us have heard of the f of x notation before, but some of us haven't. If you have it as f of x notation and you do what's called the first derivative at a particular time, it would do the same thing for us. But we're not in a calculus class, and this is something that we could do if we had the skill set for it, but we don't. So we have to use this approximation method. This is a very human method, and it's totally valid. So I want to scroll/slide this away, and I want to look at how this could be related to acceleration. Now again, for this course, we're going to assume that all of the acceleration that does happen is uniform. What that means is that if something is accelerating, it's always going to accelerate at the same rate, or else it's not going to accelerate at all. And that's a grade 11 assumption. If something has a non-uniform acceleration, that would mean that it's accelerating at a rate and then changing that rate and then maybe slowing down at a different rate over the course of one motion. And when something changes acceleration, it's the rate of change of acceleration, which has its own name. Because we've talked about rate of change of position as being velocity. We've talked about the rate of change of velocity as being acceleration. The rate of change of acceleration is called a jerk. And that, like, it sounds like that's not going to be a technical name for something, but if you ever drive in a car and it's got jerky motion, it's because somebody's turning the gas on and off, or they're hitting the brake continuously, and the acceleration rate is changing over and over again. Jerky motion really is like pretty close to a technical term being correctly used. You're jerking around. All right, so acceleration. If I have V1, let's take stock of what we know. V1 is equal to, what was it, 7.0 meters per second. And we said it was positive. I'm not going to write the letter N for north. We said that V2 was equal to, I'm going to use the unrounded value because if I'm propagating values, I always want to use the unrounded value for future calculations. I never use the rounded one. So 13.75 meters per second. T1 and T2. Well, let's talk about this. What we declared was that those velocities, V instantaneous 1 and V instantaneous 2, happened at 6 seconds and 10 seconds respectively. So then T1 would be what? When did V1 happen? 6 seconds, yeah. T2, of course, then must have happened at 10 seconds. And we had a formula for acceleration. The formula goes like this. Acceleration, assuming that the acceleration is uniform, would be equal to delta V over delta T, which could be expanded out to being V2 minus, V1 divided by T2 minus T1. And then if I sub in those values, the acceleration would be equal to, okay, V2, 13.75 meters per second, V1, 7.0 meters per second, T2, 10 seconds, T1, 6.0 seconds, and a little bit of help from the calculator people. Give me like an unrounded value, give it to me like to 6 decimal places. Who's quick on the draw? So 13.75 minus 7.0 divided by 4. All right, we got it in the front row. We have 1.6875. Do people agree? Yes? Anybody else have a calculator? Now be careful, because it's meters per second in the numerator divided by seconds. And what did we say that simplifies to? Meters per second squared. So I'm going to round this one off to 3 sig figs. Oh no, it looks like it's going to be 2 sig figs. So approximately 1.7 meters per second squared. And because it's positive, we can still say that it's accelerating towards the north. And if you're not quite sure about why it's squared, remember, meters per second divided by seconds. Really, that seconds could be expressed as seconds over 1. And if I have a fraction divided by a fraction, it's meters per second times, invert the second fraction, 1 over seconds becomes meters per second squared. Okay, so just to make sure that we definitely got the case closed on that one. I'm going to stop there.